Student, welcome to the lecture series of nanotechnology and material science. Today we are covering very important wet chemical solution processing technique for preparation of nanomaterials, and this wet chemical solution technique is known as sol gel process. So, as I said, the sol gel process is the one of the very important wet chemical solution technique for the fabrication of nanoparticles, nano rods, nano wires, and nano pillars, and even also this method is used for the preparation of quantum dots. Okay, apart from the preparation of the nanoparticles, sol gel process is also an important process for the fabrication of micro and ultra thin films. So this technique is also used in preparation or fabrication of the ultra and micro thin films. Dear student, it is quite obvious from the name of the process, sol gel process, that the sol gel process derives from the fact that microparticle or molecules in a solution, they basically agglomerate under the controlled physical and chemical environment, and then they eventually, after the agglomeration, they are linked up, and then after linking and forming a gel, these macro or micromolecules are basically heated up and converted into a nanoparticles. Okay, so basically the this the definition of the sol gel process is basically a formation of a sol with a connect of a network of gel. Okay, and then after connecting a network of gel, the material is basically heated up, and with the heating of the material or precursor material with a net, the with the gel, the extra gel, which is usually a polymeric, is just removed, and at the end of the day we got a nanoparticle. Okay, and in this way we can also uh, prepare with this process nano rods and even nano wires. But dear student, please note that there are different additional processing steps required in order if you want to prepare nano rods, nano wires, and also quantum dots. Though these preparation steps are not will not be discussed in this lecture, but in next lectures I will briefly explain that how we can produce quantum dots, nanorods, and nanowires from the sol gel process. But in simple word, in case if you want to produce a nanodot with a sol gel process, as you know, the nanodot is a nanoparticle with very small dimension. It's around 1 to 10 nanometer and even less. So in order, if we want to produce a quantum dot, we need different types of surfactants and chemical reagents, and on the basis of those we can basically control the size of the nanoparticle at very small scale. And in the case of nanorods, we need different types of layering setups or different types of gelling setups, like mesoporous silica, whose dimensions are in the range of few nanometer, and the length is around hundreds or even more micrometer. Okay, so this means that we need different types of prototypes for producing a nanoparticle, quantum dot, nanowire, and nanorod from the sol gel process. Okay. Dear student, please note that a sol gel process is a relatively new processing technique to the industry, and it is a very important part of the abrasive powder manufacturing industry, optical fibers, microelectronic industry, and it is also an important part of coating industries. Okay, the student, please note that the sol gel process is used in a two ways. One way of sol gel process is known as colloidal sol gel process, and the other way in which sol gel process is used is known as polymeric or alk oxide sol gel process. Okay, please note that the difference between colloidal sol gel process and alk oxide or polymeric sol gel process is just due to initial starting precursor material. Okay, so in polymeric process usually the polymers are used, whereas in colloidal process different types of uh, nitrate salts or different types of chloride salts are used as initial precursor material for producing final nanoparticles, nanorods, or nanowires in sol gel process. Okay. So the student, basically the sol gel process is a wet chemical solution process where the sols start to grow in a chemical solution through a hydrolysis or polymerization reaction and tends to produce a chain integral network which is known as a gel, and at the end converted into a nanoparticle and thin film. So if I define the sol gel process in simple words, the sol gel process is basically a wet chemical solution process. Okay, so this process basically involves a, wet chemical solution. It usually it may contain different types of solvent, and it also usually contain a water. So this is basically a wet chemical process in which different types of precursor materials, they could be a kind of nitrites or chloride salts and also polymers, are incorporated into a solvent. Okay, the solvent usually used in sol gel process is water. So when these precursor are incorporated into a wet solution, they basically they form a chemical solution. Okay, and this process is done under a high temperature. Usually temperature is around 250 degrees centigrade to 400 degrees centigrade. This is a common temperature for sol gel process. There is a possibility that we process the sol gel solution in very low temperature from around 100 degrees centigrade to 400 degrees centigrade. So when the chemical solution is heated, there occur hydrolysis and also a polymerization due to a polymer which is present inside a sol gel solution. And due to hydrolysis and polymerization, they the sol which is basically a particle, a precursor particles, they form a network of a polymer in the form of an integral gel. Okay, so they connect each other in the form of gel, and this sol gel material is basically heated, and due to heat the connected structure converted into a solidified particle. Okay, these solidified particles are further heated, um, and they are converted into a nanoparticles. Okay, and in the case if you want to produce a thin film via sol gel process, the initial chemical solution which basically is passed through hydrolysis and polymerization is taken off, and that is deposited onto a substrate, and that substrate is heated and converted into a thin film on it. So in a simple word, if I want to explain a soldier process, soldier process is a wet chemical solution process for a production of a nanoparticle and as well as thin film by forming a sol and gel network via hydrolysis and polymerization. Okay, and with and after the formation of after the material process precursor material go through hydrolysis and polarization are heated up and converted into a nanoparticle and thin film. Okay, so dear student, sol-gel is a wet chemical solution method where sol start to grow in a chemical solution through hydrolysis and polymerization reactions tend to produce a chain integral network which is known as a gel, and at the end converted into a nanoparticle and thin films. Okay, dear student, please note that both the colloidal routes and and as well as polymeric route for the sol gel process involve a suspension or dissolving of a precursor material in a liquid. Okay, so both routes of sol gel process, which are colloidal route of sol gel process or polymeric route of sol gel process, basically they dissolve a precursor material which is in the form of a salt, or it could be in the form of a polymer, or dissolve in a liquid solution or liquid medium. Okay, usually in colloidal processing soldier route, the liquid used is water. Okay, and whereas in polymeric route of soldier process, the liquid used is usually alcohol. Okay, so the initial solution, the precursor material is dissolved in either in a water or in an alcohol uh, solvent. Okay, and then the solution of the precursor is then activated by addition of additional acids. Okay, so the chemical reaction is basically activated in sol gel process, and additional uh, acid or base, usually most commonly used hydrochloric acid, and whereas sometimes potassium hydroxides are used to activate the chemical reaction in sol gel process. So the activated precursor then react and they basically form a network of the gel. Okay, this network grows and with ages and time. Okay, so and at this point, when the viscosity of the liquid increases at an exponential rate until the gelation occurs, and that is no more flow is observed, at that time the material is basically converted into a nanoparticle and thin films. So Please note that the in Sol-Gel process, first we use two types of uh, uh, solvent material. One is known as water and the other is known as alcohol. If we are going through polymeric sol-gel route, we use alcohol as a solvent material, and if we are going through a colloidal sol-gel process which use minerals like chlorides or nitrates, then in this route water is used as a solvent. And when the chemical precursors are incorporated in solvent, water or alcohol, the chemical precursors are very slow in reaction. In order to increase the chemical reaction, the additional reaction increasing materials like a acid like hydrochloric acid and or a basic materials are basically incorporated in a solution, and in this way the network of the gel, sol and gel form at a specific physical condition of temperature and as well as pressure and time. And when the network is formed and the viscosity of the sol and gel network is increased, at that point there occur a formation of a nanoparticle. That is an initiation point for the formation of the nanoparticle. And at the same point where the viscosity of the chemical solution increases in sol gel solution, we basically produce thin films, okay? And that at that point basically this material is removed and that material is heated at higher temperature. The chemical solution material, which is a highly viscous sol gel, is heated at very high temperature, and at that time we basically evaporate the additional extra alcohol which is act as a solvent or water, and at the end of the day we get nanoparticle. And in case if you want to produce a thin film via sol gel process, we basically remove the highly viscous solution and deposit it on a substrate, and that substrate is heated, and at the end of the day the additional solvents like water and alcohol are evaporated and we get finally highly smooth thin film. Please note that sol gel process is based on inorganic hydrolysis, polycondensation, chelation, aging, drying, calcination or sintering and crystallization. Okay, so dear student, the sol gel process initially involved inorganic hydrolysis. The word hydrolysis basically mean a breakdown of a chemical compounds due to reaction with a water. So as I have discussed that one of the root of the sol gel process is colloidal route of sol gel processing. So in colloidal routes, usually nitrates or chloride salts are used. These nitrates or chloride salt basically react with water molecules and they basically result into an inorganic hydrolysis. Okay. And this inorganic hydrolysis with time and temperature result into a gelation, and gelation is usually formed due to an interconnecting network, and this gelation basically is become more viscous with a time. And when the viscosity of the solution increases, then this viscous material is basically heated. They are dried around a temperature, around a boiling temperature of water, and then this dried material is further calcinated and sintered, and then they are converted into a crystal or nanoparticle. Please note that these are very important steps. Let's discuss first the colloidal route of the sol gel process. So in colloidal route of sol gel process, initially the inorganic precursor, which are basically nitrates or chloride salts, these inorganic precursors are hydrolyzed in a water, and after the hydrolysis process, these there occur a condensation, and then that precursor materials are then converted into an interconnected network of chelations in the presence of either an acidic solution or a basic solution. Okay, and then when the gel is formed, the solution is kept at a higher temperature for longer time, and after a longer time at higher temperature, which is usually a boiling temperature of water, the solution is basically converted and it is dried. Okay, and basically it's just dried, and that basically is form a kind of solid uh, kind of network of sol gel. Okay, and then this solid solution is then calcinated or sintered at high temperature. Please note that, student, like different materials have a different calcination temperature. If we want to prepare ferrites from sol gel process, the calcination or sintering temperature for ferrite is around 850 degrees centigrade. So at that temperature, the solution, which is basically in the form of a dried solid, is converted into a single phase ferrite. So basically this material is heated at 850 degrees centigrade if you want to get a ferrite. So in the same way, different types of materials or different types of nanoparticles have a different sintering and calcination temperature. So it will depend on the material which we want to prepare. So we will sinter and calcinate the sol gel material at that temperature, and after sintering and cancellation, the sol gel which is in the material which is in the form of solid is converted into a single crystalline material, which is usually in a form of a nanoparticle. Okay, however, in a case of a sol gel process with a polymeric precursor, we basically incorporate a polymeric precursor in usually in a solvent like alcohol, and then it is converted with the heat into a gel, and this gel, the viscosity of this gel is increased by keeping the solution for longer time at drying temperature, and after getting a dried material, there occur a calcination or a sintering to get a single phase material or nanoparticle, and at the end of the day we get single crystalline nanoparticle. Student, please note that the most interesting fact in sol gel process is the calcination or sintering temperature, because the calcination and the sintering temperature decide the nature of the nanoparticle. In case if we want to get a single phase nanoparticle, we need a temperature, calcination or sintering temperature in the range of a single phase material temperature. Like for ferrite, the minimum threshold usually used for production of a nanoparticle of ferrite is around 800, between 800 degrees centigrade to 900 degrees centigrade. So this temperature is, so this calcination and sintering temperature is very important for getting a single phase material. There are some variation in used in soldier process through which we can even get a single phase nanoparticle at very lower sintering and calcination temperature, but we will discuss those in other lecture when I will discuss about the production of the nanoparticles via sol gel process. So I will briefly explain the sol gel processing of few nanoparticles like ferrite nanoparticle or Precursor nanoparticle or Villiers phase nanoparticles at different calcination on sintering temperature, at low and high temperature, how we can produce those particles at different temperatures. Another fact to note in sol gel process is a pH value of solution. The variation of pH solution in a sol gel process may cause an agglomeration in the solution. So we have to consider all those facts like a processing temperature, like a calcination or a sintering temperature, and also a pH value of the solution of the sol gel processing systems. Dear student, welcome to the part 2 of lecture series of sol gel process. Dear student, what do you think what the term sol mean in sol gel process? What is sol? Basically, a sol is a liquid, okay? It is a chemical solution that consists of a solid dispersed colloidal suspension in a continuous liquid medium. So the student sol is a chemical solution. It consists of a solid dispersed colloids, and these dispersed colloids are dispersed in a liquid dispersion medium. Okay, so as you know that in sol gel process we initially incorporate a chemical precursor in a liquid solvent. Okay, so the chemical precursor in liquid solvent react and they are in a solid phase as a dispersed colloid in a continuous liquid solvent. Okay, so this solid medium and a continuous liquid medium, or this solid dispersed colloids in a continuous liquid medium, is known as sol. Student, please keep in mind that the sol is basically it's a liquid state of colloid solution, and the the sol don't have a kind of specific, and they don't have any type of structure. Okay, so basically this they are just a solid dispersions of colloids or uh, particles or nanoparticles in a chemical solution. Okay, another interesting fact about a sol is that sol are stable and they show Tyndall effect. Okay, this is an interesting property of the sol in sol gel process. So just what do you think? What is the Tyndall effect? Tyndall effect is an effect of light scattering. Effect of the light scattering by a particles in a colloidal solution. Okay, so basically in Tyndall effect the light is scattered by a sol in a liquid. Tyndall effect is also known as Tyndall scattering effect or Tyndall scattering. It is similar to the Rayleigh scattering, in which the intensity of the light scattered is inversely proportional to fourth power of wavelength. So this means that the blue light is scattered much more strongly than the red light in the Tyndall effect, and the same effect is followed by a sol in a sol gel process or in a sol gel liquid. So dear student, in a simple word, a sol is a colloid made out of a solid particle in a continuous liquid medium. Okay, sol are stable and they show Tyndall effect. Artificial sol may be prepared by dispersion or condensation. The dispersion techniques include grinding solid of colloid dimensions by ball milling process, etc. So just for simplicity, a sol has a generally a liquid medium, and in this liquid medium a solid colloidal suspensions are dispersed, and these solid colloidal suspensions basically follow a Tyndall effect or effect of the scattering of light, and they can easily be visible. The solid particles or colloidal suspensions can easily be visible by just scattering a light or by falling a light onto a solution in which sol is present. So, student, in simple word, sol generally has a liquid dispersing medium, whereas a solid is a dispersed phase. It can be explained in a simple word. Sol has a liquid dispersing medium, and this liquid dispersing medium is usually solvent, and the solvent may be water or as well as uh, alcohols. Okay, and in this liquid precursor medium, solid phase uh, solid phase precursor material are dispersed, and these solid phase precursor materials are basically follow they follow the Tyndall effect or Tyndall scattering. So the student, a sol basically contain a uniformly dispersed solid particle in a liquid solution. So now let's discuss the properties of the sol. Okay, basically a sol is a consists of a solution which act as a dispersion medium in which the solid uh, particles or solid material is basically dispersed uh, heterogeneously. Okay, so the sol is a mixture of a solid and as particle and as well as a liquid phase, and both of these, the solid particle and the liquid phase, they are heterogeneous and the mixture is not continuous. Okay, so they have a different composition of a solid and as well as liquid phases. The size of the sol, basically this solid particulate, vary from 1 nanometer to 100 nanometer. So basically the sol in this solid particulate in a solution of the sol have a size around 1 to 100 nanometer. Please note that there is no specific shape or a structure of a sol in a solution, but and as a whole the sol is a mixture of a solid and as well as a liquid phase, and that mixture is heterogeneous. Sol show Tyndall effect. Like if the light is passed through the sol, the light is scattered by the solid phase of the sol. So they basically mm, act and they basically follow the Rayleigh scattering law. Okay, sol are quite stable, they do not settle when left undisturbed. Okay, these solid particulate in a solution of the sol gel is processing, they remain stable even if they are left for longer time. Okay, the solid phases, which is basically act as a dispersing medium, is which basically act as a dispersing medium in a dispersed liquid phase. They act they are they do not settle down at the bottom, they are continuous throughout the liquid phase in a sol, and they remain undisturbed even for longer time. So now students, what do you think, what is gel in a sol gel process? Dear student, a gel in a sol gel process, sol becomes solid gel. So basically a sol, as I have previously discussed, is a combination of a solid medium dispersed in a liquid phase. So when a sol in a sol gel solution become a solid gel, this is done when a solid nanoparticle dispersed in a solution join form a network of particles. Okay, the solid phase in a solution, these are the solid particulate, in a solution, they join and they form a network, and in this way they form a gel. Dear student, please note, a sol is basically is a combination of a liquid solution with a dispersed solid uh, phase, okay, or solid particles. So now when the temperature of the solution increase, the solid particle start to gel, they start to combine, okay, and then they convert this liquid solution into a solid phase, and in this way they form a network, and this network is in the form of a solid phase is known as gel. So in a summary, a sol gel is a wet chemical solution process where sols start to grow in a chemical solution through hydrolysis and polymerization reactions. And after the hydrolysis and polarization reaction, the salt tend to produce a chain of integral network which is known as gel. And at the end of the conversion of a gel network into a nanoparticle and thin film. So, dear student, in a simple word, in a sol gel process, initially a precursor material is incorporated into a liquid solution or liquid solvent. The liquid solvent is usually alcohol or water. So when the chemical precursor are incorporated into a liquid solvent, those chemical reaction precursor under a physical conditions like temperature and pressure are converted into a solid phase and liquid phase material with they known as a sol, which follow a Tyndall effect. So when the sol is formed after increasing temperature and after a specific aging time, the sol start to grow, and they basically pass through hydrolysis and as well as polymerization reaction inside the chemical solution. And due to hydrolysis and polymerization reaction, the sol is basically is converted into an integral network of gel, or in a simple word, sol form a network of gel. So basically the sol which in a solid phase get connected with each other, and they nucleate and they interact with each other, and in this way they form a gel. And after the formation of the gel, the viscosity of the chemical solution of the solvent processing just increase, and then with further increase in temperature, the solid phase become more obvious, and the liquid phase of the solid solution get disappeared, and the material is then converted into a nanoparticle and as well as thin film. So in order to get a nanoparticle in sol gel process, the chemical solution, which consists of a network of a gel, is heated at higher temperature around the sinking temperature of the material, around 800 degrees centigrade or even more, and then that material is converted into a nanoparticle. Please note that there are now some soldier processing introduced, uh, which can basically produce a nanoparticle even at a lower temperature, even around 100 degrees centigrade. However, most commonly for the formation of the nanoparticulates in sol-gel process, higher sintering and annealing temperature around 700 degrees centigrade to 900 degrees centigrade is used. In case of formation of a thin film from sol-gel process, the dense gel solution is taken off from the solution and is basically dispersed on a substrate, and then that substrate is heated and the liquid phase of the solution is evaporated and thin film at micrometer scale or nanometer scale is obtained. So in a simple word, in sol-gel process, initially a precursor material is dispersed in a solution where the chemical hydrolysis takes place. Basically, as you know that in a sol-gel process, usually the salts are used like nitrates or chlorides. Salt are used. When these nitrates or chloride salts are introduced into a water which act as a solvent, so these chlorides or nitrites are basically converted into hydroxide and acidic medium. Okay, so they basically go through a hydrolysis process, and due to hydrolysis and polymerization of the chemical solution, they basically form a sol, and that sol basically after a heating and aging, the sol is converted into an integral network of gel. The gel is basically produced due to increase in viscosity of the solution of the sol, and at the end the gel is converted into a nanoparticle at higher temperature, higher annealing or sintering temperature, or even a drying temperature of the solution. And in case of the thin film, the viscous solution of the sol is of the gel is introduced onto the surface of the substrate, which is heated and annealed and converted into a thin film. Dear student, welcome to the lecture series of Sol Gel Processing for Nanomaterials and Thin Film Synthesis. So today, in this lecture, I will briefly explain step by step the processing step involved in Sol Gel process. So the student, I will briefly explain one by one in a very simplified way that how the sol gel process take place. Okay, what are the steps involved in sol gel process for the synthesis of nano particles, nano wires, nano pillars, and also for the fabrication of the sol gel processed thin films. Dear student, the first step of the sol gel process is the selection of the precursor materials. Okay, so every types of chemical solution process, every wet chemical solution process like a sol gel process or chemical co-precipitation method, every type of chemical solution or wet chemical solution method required a specific type of precursor selection. So student, most commonly there are two types of precursor used in sol gel process. The first type of precursor is known as metallic alk oxide. Some of the common types of metallic alk oxide used in sol gel process are titanium alk oxide, chromium alk oxide, and zinc alk oxide. So basically, Most commonly, the transition metal oxides are uh, commonly used in sol gel process. Like, if we use titanium alkoxide, this type of transition metallic alkoxide is most commonly used for the fabrication or for the synthesis of titanium oxide nanoparticles. Similarly, chromium and zinc oxides are used for the synthesis of the chromium and as well as zinc oxide nanoparticle. Please note that, dear student, the titanium alkoxide, chromium alkoxide, or any different types of transition metal alkoxides may be used in synthesis or in fabrication of complex oxide structures like ferrites. They may be used in the synthesis of Arvelius phase materials like Bi6, Ti3, Fe2, O18s, like layer structures of transition Arvelius phase nanoparticles and thin films. So the metallic alk oxides are now limited to the synthesis of just their oxides like titanium oxide, chromium oxide, or zinc oxide nanoparticles, but they may be or they are broadly used in synthesis of complex structured nanoparticles. The key aspect to notice here is that the alk oxides are more commonly are used in polymeric route of sol gel process. So they alk oxide are not used in uh, another route of sol gel process, which is a colloidal route of sol gel process. So in order to use the colloidal route, there are different types of metallic precursor used for the fabrication, inorganic metallic precursor used for the fabrication of nanoparticle in um, the second route of the synthesis of nanoparticle, or a colloidal route of the synthesis of the nanoparticle. Because the key difference in metallic oxide and the other inorganic precursor is just the solvent which is used uh, in the sol gel process. For metallic alkoxide, the solvent used in sol gel process is usually alcohol, whereas if the sol gel process is using inorganic salts, so they usually used water as a solvent medium. So, student, the second type of precursor used in sol gel process are inorganic salts. Most commonly used inorganic salt in sol gel process are metallic chlorides. These chlorides are usually zinc chloride, calcium chloride, magnesium chloride, chromium chloride, or cobalt chloride. So these metallic inorganic salts are usually used in colloidal route of sol gel process, and because these metallic inorganic salts basically go through a hydrolysis process, and due to a hydrolysis process they are converted into a well dispersed colloids. So due to this, in sol gel process, metallic chlorides are used as a precursor material in colloidal route of sol gel process. Another type of metallic inorganic precursor used in sol gel process are metallic nitrates. Usually these are transition metallic nitrates. Some of the common example of metallic nitrates used in sol gel process are lithium nitrates, potassium nitrate, cesium nitrate, zinc nitrate, magnesium nitrates, and many more. So all these, whether they are metallic chlorides or metallic nitrides, they are the essential part of colloidal route of sol gel process, and they are used as an initial step for the selection or of the precursor for the sol gel process. So dear student, the second step of the sol gel process after selection of the precursor material is hydrolysis and polymerization of the precursor material in solvent. So basically, in case of uh, polymeric route of sol gel process, the metallic alk oxides are polymerized or hydrolyzed in alcoholic solvent, or and similarly in case of a colloidal route of sol gel process, the inorganic metallic precursor in second step are hydrolyzed in water, which act as a solvent in a colloidal route of sol gel process. So dear student, the precursor material in case of multi-component precursor material like this and this and this are introduced in a liquid medium. It could be a polymeric medium or organic medium like alcohol, or it could be a water uh, which is act as a which used as a solvent in a colloidal processing route of the sol gel process. So if I these different types of round ball are basically representing a multi-component or multi precursors or different types of precursor which we are basically incorporating in and for hydrolysis in step 2. So this is just a graphical representation of multi precursors used in a sol gel process. So these multi precursors in the sol gel process in step 2 of the sol gel process are hydrolyzed in a water, or if they are alkoxide, then they are hydrolyzed and polymerized in organic solvent like alcohol. Okay. So the student, in a second step of the hydrolysis process, we basically introduce a heat treatment setup, and which is usually a heater, and the liquid solvent is placed on the heating plate or hot plate. Okay, in case if we are using polymeric route of sol gel process, we use organic solvent like alcohol. Okay, or in case if we are using colloidal route of sol gel process, we use uh, water. Okay, which is usually a deionized water. So in this solvent, basically, uh, there is also a setup of a stirring. Okay, so the precursor of multi-component compounds are like zinc chloride, potassium chloride, copper chloride, or alk oxides like titanium alk oxide, zinc alk oxide for our polymeric route, are introduced into a solvent. Okay, and this solvent is in the precursor material, uh, if organic or inorganic precursor material, is heat treated and it is stirred on a hot plate which have a setup of temperature and as well as rotation. Okay, so the chemical precursor which is incorporated in solvent in step 2 of hydrolysis is basically heat treated and also it is stirred. So due to a heat treatment and stirring there will occur hydrolysis. Okay, and hydrolysis is basically a formation of hydroxyl groups. Okay, and there will also occur polymerization in case of polymeric route of sol gel process. So dear student, please note that the stirring rate and the temperature of the solution are play vital role in case of preparing nanoparticles and thin films. The faster is the stirring, they will affect the size of the colloid and also the distribution of the colloid in the solution. And similarly, temperature of the solution will also play a vital role in order to formation of the agglomerates. Okay, higher temperature of the hot plate may cause an agglomeration or of the agglomeration of the particle or colloid inside the solution. So both the temperature and the stirring rate in step 2 of the soldier process, which is hydrolysis and polymerization, are considered. Okay, usually the hydrolysis in soldier process take place around 300 degrees centigrade. It could vary, it could, like the heating temperature of hot plate could vary from 200 degrees centigrade to 300 degrees centigrade, but usually uh, in research a lot of hydrolysis of the in solid process is usually taken around 300 degrees centigrade. So the temperature of the hot plate in solid process is usually kept around 300 degree centigrade, whereas the stirring rate may vary. It could be around 1000 rpm. So it's depend on the requirement of the process. Okay, so due to heat treatment and stirring of the precursor material in a solvent, they will result into a hydrolysis and polymerization. Okay, so and due to a heat hydrolysis and polymerization, the precursor materials are basically converted into a sol. Sol, as I have previously discussed, they are well dispersed particles in a range from 1 to 100 nanometer. So the sol is formed during the hydrolysis and polymerization of the sol gel process. So dear student, what do you think what the term hydrolysis mean? Basically, the hydrolysis is a chemical breakdown of the precursor material due to a reaction of a solvent water. So these precursor material in hydrolysis process of the sol gel route, they will be converted into hydroxyl groups, okay, and as a result they will form a sol, and the sol will is basically a dispersed a nanoparticle in a liquid medium, and these dispersed nanoparticle basically are well arranged, and they follow the one of the most common effect known as a Tyndall effect of the reflection of light. So in hydrolysis process, in chemical in sol gel, in hydrolysis step, the precursor material is basically in a solvent is converted into a hydroxyl sol, okay. So the sol is formed in hydrolysis and polymerization step of the sol gel process. So just keep in mind that the temperature and the pH value of the chemical solution in hydrolysis process play a vital role. The yellow one is basically representing a thermometer, whereas this pink line is basically representing a pH meter. So they are both the temperature thermometer and pH meter are used throughout the sol gel process to monitor the temperature and as well as the pH value of the chemical solution used in sol gel process. So please note that the variation of the pH value of the solution basically is affect the size of the particle or the size of the sol. So acidic medium or basic medium of the solution basically affect the size of the nanoparticle. And similarly, the temperature is monitored by this thermometer, and the temperature also affect the size of the sol inside the solution, because if the higher is the temperature, there will be a higher rate of the agglomeration of the sol, and at the end of the day with the sol gel process we will achieve nanoparticle with a higher size. So both the temperature and the pH value of the solution play vital role in sol gel process. Another important effect to notice here in a hydrolysis step is stirring rate. So the stirring rate, a higher or low stirring rate, will result into a uniformity of composition of the nanoparticles and also the size of the nanoparticle, okay. So if the stirring rate is higher, the hydrolysis will be throughout the solution, and the sol particle will be uniform in composition throughout the solution, and similarly the higher rate will also result into a smaller size of the nanoparticle. Dear student, please note that there in at advanced level there is a possibility to incorporate a surfactant inside the chemical solution during the hydrolysis and polymerization step of solvent process. So the surfactant basically cover the sol, okay, around and the hydrophilic or hydrophobic part of surfactant cover this the sol throughout, and due to this the size of the nanoparticle is controlled. So if we want to prepare a very small nanoparticle in sol gel process, surfactant are incorporated inside the solution of the sol gel process in hydrolysis step. Dear student, please note that in order to fasten the rate of the chemical reaction in sol gel process, usually the basic like basic like potassium hydroxide solutions or the acidic solution like HCl or hydrochloric acids are incorporated in a sol gel solution. So now just to consider the sol gel third step of sol gel process uh, by a schematic diagram. So this image basically represent an hydrolysis of the sol gel solution, and due to hydrolysis, which is basically, and polarization, which is basically a second step of the sol gel process, there occur a formation of sol inside the solution. Okay, sol is basically a dispersion of the a uniform well stable nanoparticulates inside the chemical solution. Now student, please note that the interesting fact to notice here in third step of the sol and gel formation in sol gel process is the incorporation of chelating agent. Chelating agent is very important in order to control the size of the synthesized nanoparticle inside the solution. Most commonly used gelatin agent in sol gel process are usually diamine solution or dicatonate. Okay, so they basically donate electron at different positions. Usually have two positions at which they donate electron to a transition metal ion. Okay, so in this way they basically also control the hydrolysis and condensation inside the sol gel solution, and in this way the size of the particle in sol gel solution is controlled. So student, when the gelatin agent is incorporated inside the sol gel solution and the temperature and as well as pH of the sol gel is solution is controlled, they result with a time a formation of a wet gel, which is represented by a schematic diagram is this. So basically the sol inside the solution, they basically are interconnected uh, in the form with a gel, and they form a link of sol and gel inside the solution. What do you think, student? How the wet chemical gel or sol gel or gel is formed inside the chemical solution? Number one is the incorporation of gelatin agent, which control the size of the sol inside the solution. And number two is basically a temperature of the chemical solution and also the pH of the chemical solution. And the third one is the time or aging of the chemical solution result into a formation of a link of a sol in the form of a gel inside the chemical solution. Okay, and this gel is known as wet chemical or wet gel inside the sol gel solution. The student, please note that wet gel is an interconnect gel of sol and gel, or it is a network of a sol and gel inside the solution, inside the sol gel solution. Now, interesting fact here to notice is that how the wet chemical uh, gel is converted into a nanoparticle. Okay, so this the wet chemical gel play very important role in order to convert it into a thin film. And similarly, in order to make and convert the wet chemical gel into nanoparticle, they are basically heated or annealed and sintered at higher temperature. So, please note that the viscosity of the solution in sol gel process also play a vital role in formation of nanoparticles. Okay. So usually in thin film, the viscosity and the solution of with less viscosity is considered to form a thin film, whereas in the case of nanoparticle, the temperature and aging time is further increases and the solution is basically dried and converted into a nanoparticles. So, dear student, the fourth step of a sol gel process is heat treatment and dry gel formation. Please note that the this fourth step of the sol gel process is usually used uh, in formation of a nanoparticles. Okay, so nanoparticles are processed by using a fourth step of the sol gel process. So in fourth step, the chemical solution which is present in a form of a sol and which is present in a form of a wet gel is heat treated, and due to a heat treatment the wet gel is converted into a dry gel. This can be or this may be represented by a schematic diagram as. So basically this is a chemical solution. Okay, and inside the chemical solution there is a network of a wet gel, which is basically it is a gel with a solvent. Okay, usually the solvent is water, but in polymeric sol gel process the solvent will be alcohol. So the wet gel is basically in sol gel process present in sol gel process uh, is present in solvent, and the solvent is either water or alcohol. Okay, so now this wet gel, if we want to prepare thin film, then we use this wet gel on a substrate, and that is heat treated and converted into a thin film. However, here we are going to prepare a nanoparticle from this wet gel. So in order to prepare nanoparticle from this wet gel, we convert this wet gel into a dry gel by heat treatment. and this dry gel is represented by a schematic diagram is. So dear student, this is a dry gel. So this dry gel is prepared after the heat treatment and the additional solvent is evaporated or removed. Usually the dry gel is prepared by soft baking process. Basically, the chemical solution which composed of a liquid or wet gel is evaporated at a temperature slightly above the room temperature for longer time. So when the solvent material is placed at a temperature higher than room temperature for a longer time, the solvent inside the solution is just evaporated, and as a result a wet gel is basically achieved, and the rest of the solvent is just evaporated. Dear student, please note that usually, especially in organic route of sol gel process, there are different types of organic compound still present in the dry gel. So in order to prepare a nanoparticle, the wet gel is sintered at very high temperature and it is annealed for long time. Okay, the reason for annealing is just to remove the residual impurities which are present in the dry gel, and after a heat treatment at high temperature, like by doing annealing and sintering, we basically achieved nanoparticles. The student, please note that these physical conditions play a very important role in order to prepare nanoparticles. The, because the sintering and annealing temperature are the key in order to get a single phase material. Please note that nanoparticles have a specific structures. So every material have a different sintering and annealing temperature. They require different sintering and annealing temperature in order to get a single phase nanoparticle. So the physical parameter like sintering and annealing temperature are playing vital role in order to get a single phase nano particle. Okay, so please note that when the dry gel is annealed and sintered, we get uh, we get a dry types of structures, and they are indeed a nanoparticle, but still we need piston and mortar to crush them further and produce and convert them into a single phase nanoparticles. Okay, so the role of the sintering and annealing in sol gel process play important role in order to achieve a single phase material. Okay, if like let's say if we are interested in producing iron oxide nanoparticle, usually they are sintered and annealed at higher temperature, because the single phase of iron oxide Fe3O4 nanoparticles are usually achieved around 800 and between 800 and 900 degrees centigrade. So annealing temperature for such material is higher. Okay, if we anneal the iron oxide nanoparticles below the single phase formation temperature, like below 800 degrees centigrade to 900 below 800 degrees centigrade, this will result into a formation of impure iron oxide nanoparticle. So in order to produce a single phase nanoparticles, we need a specific sintering and annealing temperature. Okay, so after like sintering the material, dry gel, we get a single phase material, and that single phase material is further converted into a nanoparticle by doing a mechanical milling by using piston and mortar. Like the material which we achieved, a dry material which we achieved after sintering aniline is crushed and converted into a nanoparticle by using by using a ball milling or mechanical milling, like using a piston and mortar. So with that we basically achieved a nanoparticle. So different in order to achieve thin film via solid process, the third step of the wet chemical, the third step, which is known as a wet gel formation, is used, and it is basically diverted in order to get a thin film via sol gel process. So in next slide, I will explain that how we can basically modify a third step of solid process, which is basically a wet gel, and how we convert it into a thin film. Okay. Let's discuss how the thin film is produced by a sol gel process, and like how we can get thin film by a sol gel process. As I have previously discussed, the third step of the sol gel process is sol and gel or wet gel formation. Okay, just for a memory, if the first step of the sol gel process is precursor selection, the second step of the sol gel process is hydrolysis and polymerization. So in third step of sol gel process, the solution which is hydrolyzed and polymerized is basically uh, heat treated, and it is converted into a wet gel. So this wet gel play a vital role in order to achieve a thin film via sol gel process. Okay. And so the student, please note that when we achieved a wet gel uh, in a third step of sol gel process, we just take that wet gel and take it onto the surface of the substrate. So there are different types of techniques which are used to deposit that wet gel onto the surface of the substrate. One of the most commonly used technique to deposit a sol gel thin film or wet gel of the sol-gel solution onto the surface of the substrate is known as a spin coating. Okay, so in spin coating process, the chemical solution, which is in the form of a wet gel, is taken off and it is deposited onto the surface of the substrate by using a spin coater. Okay, so this is basically a substrate, and with a spin coater, usually it is a syringe. The usually in a syringe, the chemical solution, which is usually a wet gel, is taken off on into the syringe, and then it is deposited onto the surface of the substrate. So student, please note that the physical condition used in spin coating play a very important role in order to get highly uniform thin film via sol gel process. The first and important key parameter of the spin coating is the rotation of the substrate. Okay, usually spin coater operate uh, from at a different range up to 2000 rpm. Okay, so higher is the rate of the rotation of the substrate in a spin coater will result into a better uniformity and also the thickness of the deposited solvent process thin film. Furthermore, the temperature of the spin coating setup also play a vital role in order to get a better adhesion of the deposited film with the substrate. So the spin coating method is not a topic of this presentation. So I will briefly explain that what are the physical parameters associated with spin coating of thin films in next lectures. But in for better understanding, you need to know some of the basic or key parameters important in order to get a better thin film via solder process. And these key parameters are basically the rate of the rotation of the spin coater, number one, and number two is the temperature of the substrate inside the spin coater. So these are the key important parameters in order to get a uniform thin film via solder process. Okay. So the other techniques through which are used in order to achieve a thin films via sol gel process uh, is is known as dip coating. Okay, so different dip coating is a quite simple technique. The substrate material, which is could be a silicon, it could be a glass, it's depend on our requirement that on which type of substrate we want to deposit a thin film, is incorporated inside the wet chemical gel solution. Okay, and with the different pulling rate, we basically deposit or we basically dip coat a thin film on the surface of the substrate. Okay, so different dip coating instrument setup may be explained with a schematic diagram. Okay, and the dip coating instrument consists of a substrate which is connected with a moving setup. Okay, so this is a movable kind of pulley which basically pull the substrate. Okay, and uh, the substrate may be pulled downward and it may be pulled upward. So there are the substrate in dip coating process may be pulled inside the solution and it may be pulled outside of the solution with a rotation setup. So basically in dip coating deposition of thin film, initially this is basically a wet chemical gel solution, and this wet chemical gel solution, the substrate is incorporated via dip coating setup into the wet chemical gel solution. Okay, and the then this substrate, when its substrate is placed inside a dip chemical solution, then this substrate is pulled upward, and in this way the substrate is taken off of the wet chemical jet solution, and then this substrate usually have some part of the wet chemical gel solution onto its surface, and then with the heat treatment that part of the wet chemical gel which is placed on the surface of the substrate is dried and it is converted into a thin film. Please note that, dear student, the rate of dipping or the rate of the coating of the wet chemical gel onto the substrate play a very important role in order to achieve thick, thin or ultra thin film on the surface of the substrate. higher is the rate of faster is the rate of pulling of the substrate out of the wet chemical gel solution will result into a formation of thin, ultra thin film. Whereas if the rate of the pulling of the substrate is slow, will result into a formation of thick film onto the surface of the substrate. Another parameter is of the dip coating is known as layer by layer dip coating. If we increase the number of times of insertion of the substrate into the liquid solution or wet chemical solution, this will result into a formation of thicker and well uniform film. So dear student, please note that the rate of pulling of the substrate from the wet chemical solution and also the higher number of pulling rate of the pulling of the substrate from the chemical solution play vital role in order to achieve thick, thin or ultra thin film via dip coating setup inside the wet chemical gel solution of the sol gel processed uh, uh, solutions. Okay, so basically these two key are the key physical parameter in order to get a thick, thin or ultra thin film via sol gel process using dip coating setup. Dear student, welcome to the part 4 of our lecture series about the sol gel process. In this lecture, I will briefly explain about the physical and as well as the chemical parameter involved in sol gel process. So dear student, please note that the physical and as well as the chemical parameters involved in sol gel process play vital role in order to prepare nanoparticle, nanowire and nanorod via sol gel process in controlled when manipulated way with a specific chemical composition. So dear student, please note that in order if you want to prepare nanoparticle, nanorods or nanowires, we need physical parameters like pH value of the solution which is processed under a sol gel process, also the temperature and pressure used on the solution. And the chemical parameter which involved in sol gel process is a chemical composition and the role of the surfactant inside the solution and reaction inside the sol gel process solution. So dear student, overall please note that in simple word that physical and chemical parameters in sol gel process are very important in order to prepare nanoparticle, nanorods and nanowires via sol gel process in controlled fashion in a specific chemical composition. Okay, so suppose if you want to prepare copper iron oxides nanoparticle. Copper iron oxide is basically it is a ferrite. It is a ferrite, so it's if like if you want to prepare CuFe2O4 nanoparticles. So what you need to consider in preparing CuFe2 nanoparticle via sol gel process. First of all is the chemical parameters or the chemical parameters. Then those chemical parameters will be the molar ratios of copper, iron in a solution of in the sol-gel process solution. So these the molar ratio of the initial precursor, which is based on copper and nitrogen, is considered. And the second will be the physical parameter, like will be the what will be the temperature of the solution, what will be the pH value of the solution. So all these parameters will be considered in order to prepare copper, iron oxide or ferrite nanoparticles. So same uh, types of physical and chemical parameters are considered in any type of material, which could be a nanorod, which could be a nanoparticle, which could be a nanowire, which is processed via sol-gel process. So in a simple word, physical and chemical parameters involved in sol-gel process is very important in order if you want to prepare a well precised and a better material with a very accurate composition and and also a size of the nanoparticles, so or a nanorod or nanowire. So all the physical and chemical parameters are considered, and a student must be very careful when they are processing nanoparticles, nanowires or thin film via sol-gel process. So they need to consider the physical and chemical parameter in order to get an accurate result. So dear student, as I previously discussed in processing state, that the first important aspect to consider in a processing physical and chemical parameters in sol-gel process is the selection of the precursors. Okay, so initially in sol-gel process we basically select the precursor. Please note that the precursors used in a sol-gel process are usually metallic alk oxide, or they may be a non-metallic nitrates and chloride salts. Okay, so these are commonly used to different types of uh, precursor material in a sol-gel process. As I have discussed in sol-gel processing steps, that there are two different routes used in a sol-gel process for synthesis of the nanomaterial. One route for the sol-gel process for synthesis of nanomaterial is known as a polymeric route for the sol-gel polymeric route of the sol-gel process for the synthesis of the nanomaterial. In polymeric route of sol-gel process of synthesis of nanomaterial, we usually use a metallic alk oxide as a precursor material. Okay, so this is basically an organic uh, precursor, and this precursor is usually used in a solution of alcohol or different types of organic solvents. So an example word uh, in a polymeric route of sol-gel process, metallic alk oxide is used in organic solvent like alcohol, etc. And the other route of the sol-gel process is known as colloidal route. So the colloids are produced in colloidal routes by using a non-metallic or inorganic nitrates and chloride source. Okay, so different types of transition metal nitrates or transition metal chlorides are used in colloidal method for the colloidal method of sol-gel process. So before considering the physical parameter of sol-gel process, the student must be very careful in precursor selection. So uh, if they are going to use an organic or polymeric route of sol-gel process, then they need to use a metallic alk oxides in organic solution. And if they are interested to use a colloidal route of solvent process, then they need to use nitrates, transition metal nitrates usually, and transition metal chloride salt in a water solution. So now let's discuss about the physical parameters involved when we incorporate the organic precursors or inorganic precursors in a solvent. So the first physical parameter need to be considered in a solvent process when we incorporate a chemical precursor in a solution is a chemical reaction time and the temperature of the solution. Okay, so initially in a solvent process, the precursor material, it could be an inorganic or polymeric precursor, they are incorporated in the solution in the solvent, which could be a water or it could be an alcohol or organic medium. Okay, in case if we are using a polymeric route, so when they are incorporated inside the solution, then they there with then we have to consider a chemical reaction time and temperature. Okay, so usually the solution of the solvent process solution is placed on a hot plate and the temperature is usually considered slightly above the boiling temperature of the water. It's usually used around between 100 degrees centigrade to 200 degrees centigrades. Okay, so and this when the solution is heated, there is start an hydrolysis and polymerization inside the solution. So distant, please note that if the solution is kept for a long time, there will be a change in the change inside the solution. If in case if you are preparing colloids, so if you keep it for longer time, there is a possibility of the formation of uh, as particles with a huge size. Okay, so the aging time or the time at which the processing time of the solution at higher temperature and during a chemical reaction play a vital role. Okay, so let's say if the temperature is high, there is a possibility of there is a possibility of increase in the size of the nanoparticles. Okay, and secondly, if the reaction time is also high, there is a possibility of getting a better material with a better composition. So both the chemical reaction and the temperature of the chemical solution in solvent processed solution play important role. Another physical parameter to be considered in solvent processes is chemical precursors molar ratio. Just please note that the chemical precursor molar ratio, which is basically a physical parameter which at the start of the solvent process play vital role in order to achieve desired nanoparticle, nanomaterials, or nanorods, or nanopillars. So, student, we need to consider the precursor molar ratios before starting the processing, before starting the solvent process. So, just let's explain it by example. Here I have given the example of two water molecules. So the two water molecules basically have four hydrogen atoms and as well as one oxygen atoms. So overall they are five. They are the overall they are six. So they have four hydrogen atom and two oxygen atom. They are six. So we need four ratio to two. 4 hydrogen atom to 2 oxygen atom in order to prepare 2H2O. So our initial precursor we need to use in order to prepare two molecules of water will be 4 hydrogen atom and as well as 2 oxygen atoms. So when they will combine, as their molar ratio is equal to the molar ratio of the final product of two molecules. So when both the 4 molecules of hydrogen and 2 molecules of oxygen combine, they, as a result, we get 2 molecules of water. So same case is applied for a Sol-Gel process solution. Let's say if we want to prepare copper ferrite nanoparticles. So this is general formula for copper ferrite is Cu Fe2 and O4. Okay, so this is general formula for copper ferrite. In order to prepare a copper ferrite via Sol-Gel, please note that we need a 1 molar ratio to 2 molar ratio of copper and iron. So we need to prepare 1 mole of solution of copper and 2 mole of solution of iron, and at the end of the day we need to combine both these, and at the end of the day we will achieve copper iron oxide nanoparticles or nanomaterials. So let's explain it in a brief. In order to prepare a copper iron oxides nanoparticles, we need to consider the molar ratio of copper and iron oxides. Okay, copper and iron molecules. Okay, so student, please note that usually in Sol-Gel process, copper and irons used, if we are using a colloidal route of solid process, they are used in nitrides or in chloride forms. Okay, so they are usually used in FeCl3 or Fe2NO3 form. So initially we need to use the molar solution of copper chloride and copper iron chloride uh, in a specific molar ratio of copper and iron. Okay, so usually the stoichiometric ratio of copper will be half to the stoichiometric ratio of the iron in order to prepare a copper iron oxides. Okay, so initially they will be incorporated copper oxide separately in a water solution, and similarly iron chloride will be incorporated separately in the water solution. Please note that usually in laboratories we need to prepare a very small quantity of the ferrite nanoparticles, okay, or ferrite nanomaterials. So in order to prepare small quantity, we usually consider the molar ratio 0.1 of the copper and 0.2 of the iron. Okay, and they are incorporated in 100 ml of the water solution separately. Okay, so copper chloride molar ratio 0.1, and whereas the iron chloride whose molar ratio is double and it is 0.2, they are incorporated separately in a solution, in a water solvent, in a beaker, and usually it is 100 ml. Okay, please note that the mole, if we are going to prepare 1 molar solution, we need 1 liter of the water. However, if we are going to prepare 0.1 and 0.2 molar solution of copper and iron, we need 100 ml and 100 ml of the water solution. So both the copper chloride and iron chlorides in a specific molar ratio of 0.1 and 0.2 are incorporated separately in a solvent. Okay, and then they are processed by considering the physical parameters like temperature and and pH value, etc., and then they are combined after slightly dissolving in the water. They are combined and then they are further processed for a Sol-Gel process. So dear student, in a simple word, the molar ratio of the precursor, initial precursor material, play very important role, and this is the first physical step toward the sol-gel process for the nanomaterial synthesis. I will briefly explain in next few lectures that how we can prepare different types of nanoparticles like iron oxide nanoparticles or Arrhenius phase nanoparticles via sol-gel process. So I'll consider this, that how we calculate the molar ratio of the initial precursor in the sol-gel process. Okay, so that is not a part of today's lecture, but this part will be further covered and will be briefly explained in the next few lectures. So student, another physical parameter need to be considered or play a vital role in a sol-gel process is known as chemical solution pH. Okay, please note that usually sol-gel process is done in acidic medium. Okay, and citric acid or even HCl, they are used as a chelating agent. Usually the citric acid is mostly considered as a chelating agent, and this chelating agent usually basically bind the transition metals with them. They have different two or more points which are electron donor points, and they basically bind the metallic or transition metals with them, and due to this they basically control the hydrolysis. And another aspect to note here is that the overall pH value of the in the sol-gel process play a vital role. Usually the pH value is kept around 7. It is usually kept as at 7, and solution is neutral. Like in the sol-gel process we usually use citric acid with ammonia, so the ammonia basically control the pH value, and it is kept around 7. But please note that in order to prepare a better nanoparticles with a soft gel, soft organic gel, the sol gel process is done below pH value of 3. Usually above the pH value 3, the soft gel is converted into a hard gel. Okay, so when the soft gel is converted into a hard gel, then the highly viscous material, if you want to convert into a nanoparticle, we need to sinter that material, and due to a hard gel there will be a problem in order to achieve a nanomaterial at the end of the sol gel process. So the pH value of the sol in the sol gel process is considered in an acidic medium which is below the 7, and it is usually considered below 3 in order to achieve a better nanoparticles. Another aspect to consider is that with the higher pH value, like above the 3, there is a possibility of agglomeration of the nanoparticles. So all those physical factors are considered in sol gel process. Okay, so just in a simple word, pH value during a sol gel process play important role in a nanoparticle size, nanoparticle stability, and even nanoparticle or nanomaterial morphology. So they are very vital. This physical property of this chemical solution is very vital. So for researcher, please note that it is very important to try the variation of the pH value to check that what is the impact of the variation of pH value on the nanomaterial, nanoparticle, nanowire, or nanorod size, dimensions, and length. So this factor is very important. Okay, student, please note that the sol in a sol gel solutions are thermodynamically unstable systems. Okay, they have a high free surface energy and can exist only in the presence of stabilized colloids. So in order to get a stabilized colloid, or in order to get a stabilized network of colloids inside the solution of the Soldier process, pH value basically of the solution play a vital role. And so this means that the pH value play a vital role in a Soldier process, and we Soldier process in order to achieve a stabilized nanocolloids or stabilized nanoparticle with a better morphology. We need to use a controlled pH value of the solution. As I've discussed, the, mostly the solution, the nanoparticles or nanorods or nanomaterials are prepared in Sol-Gel process in acidic medium. The pH value is below 3, but the student, just especially for the research student, just for improvement of your knowledge, and just for getting just for trying to achieve a better material, you need to try to prepare a nanoparticle with a different pH values, like from 1 to 7, or even in a basic medium. So you need to try in order to have a more knowledge about the role of the pH value in a chemical solution of this in a Sol-Gel processed chemical solution. However, um, in order to prepare a better material, as it is tried and tested, it is good to prepare to process a chemical solution in Sol-Gel process with a pH value below 3. This is another very important physical parameter to consider in a Sol-Gel process is the incorporation of chemical surfactant. Please note that usually a, the chemical surfactant is incorporated in Sol-Gel process at advanced level, because the standard of Sol-Gel process do not use as chemical surfactant, and we just prepared a nanoparticle, nanorod, or nanowire, or nanopillars with the Sol-Gel process with it uncontrolled dimension by just a normal Sol-Gel process. However, at advanced level, if you want to prepare a nanoparticle or nanorods or nanowires or nanopillars with a specific controlled dimensions, or with a specific controlled size, we need to incorporate a chemical surfactant in a sol gel solution. So please note that this is an additional type of physical parameter which is used at advanced level if you want to prepare a very ultra small or quantum dot level nanoparticle, or a nanorod or a nanowire with very small dimensions. So in that case, scientists prefer to use a chemical surfactant in a sol gel solution. Dear student, please note that surfactant play vital role in order to control the size of the nanoparticle, okay, in a Sol-Gel process. So basically, the colloid which is present in a solution of a Sol-Gel process is covered by a surfactant, okay, and by controlling or covering the colloid by a surfactant, there will be no further uh, uh, nucleation and growth of the nanoparticle. So the nanoparticle will remain small in a solution, and on the further physical step like heating, or sintering, we will at the end of the day achieve a very small size and nanoparticles. Please note that there are two different types of surfactant which are used in chemical processes. The one type of surfactant is known as non-ionic surfactant. Non-ionic surfactant used uh, in are commonly used in advanced level of chemical solution process. They are usually micro and nano emulsion process. So these processes are further advanced step or advanced processes to the solvent process. However, these may be used in a solvent process. Some of the common type of non-ionic surfactants are polyoxyethylene surfactant or sugar ester. Okay, so they are commonly used in solution based process. There are also ionic surfactant. Okay, they have ions on them, and some of the common types of ionic surfactants are biased to ethylene sulfosuccinates. So they are commonly used in solution based processes. Okay, student, please note that though the chemical surfactant are used at advanced level of solvent process, because in order to use a chemical surfactant we need also to incorporate oil in a solution. So they are not the scope of our lecture here, but I will briefly explain in especially in microemulsion process of chemical solution for a nanoparticle system, that how the role, what is the role of the surfactant, that how the surfactant control the size of the nanoparticle. So just in this uh, additional physical property of incorporation of a chemical solution in a solvent process is an additional type of parameter. Usually they are not used in solvent process, but at advanced level, if you want to control the size of the nanoparticles, we need to incorporate a surfactant in a solvent solution. Okay. The question here is this, that what are the physical parameters we need to use in order to prepare a thin film via sol gel process. So what are the physical parameters we need to control in order to achieve a thin film with a better quality and uniformity in a sol gel process? So dear student, initially in order to prepare a thin film via sol gel process with a better quality, we need to about the coating methods of thin films, like what type of coating method we need to use in order to prepare a thin film via sol gel process. Dear student, please note that in chemical solution processes there are different known coating methods used. One of the most commonly used coating method in a chemical solution deposition is known as spin coating process. Another method used to coat a sol gel solution is known as dip coating method. Okay, and dip coating method is layer by layer method. So the third type of well-known method used is known as spray coating. So mostly or commonly there are three types of method used to deposit a thin film via solder process. Number one process is known as spin coating. Number two process is known as dip coating, and number third process is known as spray coatings. Okay, so in the spin coating process, the sol gel solution is spin coated onto the surface of the substrate, and after spin coating they are heated, and at the end of the day we achieve a thin film. Whereas in dip coating, as a substrate material is incorporated in a sol gel solution and then it is dipped consecutively depending on our required many time, and after removing the substrate material it has a solution coated on it, and after heating the substrate with a coated solution we achieve the thin film. Whereas in a spray coating, the precursor material in the form of solution or as wet gel in the form of solution is injected in a syringe, and then it is spray coated onto the surface of the substrate, and at the end of the day we after heating this the substrate we achieve a thin film. Another key important parameter considered in a sol gel processed thin film is baking temperature. So student, please note that when the wet gel solution is introduced onto the top of the surface of the substrate, we need to bake the solution which placed onto the top of the substrate, and the baking temperature is usually between 100 to 200 degrees centigrade. So baking means will remove the wet part of the solution of the film, and due to this we basically get a solid thin film. Another key important physical parameter in sol gel processed thin film is annealing and sintering temperature. Please note that this is very important physical parameters. Different type of material, like if you want to prepare iron oxide Fe2O4, it has a specific phase formation temperature at which the dry sol gel is converted into a single crystalline or single phase iron oxide nanoparticle, nanorod or thin film. So annealing temperature play a vital role or sintering temperature play a vital role in order to get a highly pure single phase nanomaterial, nanowire and thin film. Okay, so as I have discussed that iron oxide have usually in a conventional solder process Fe3O4, which is basically a ferrite, its temperature is around annealing or sintering temperature for single phase formation is around 800 degrees centigrade to 300 to 900 degrees centigrade. Usually the sol gel solid form of sol gel is basically kept around between 800 degrees centigrade to 900 degrees centigrade for 30 to 1 hour, and then it is converted into a iron oxide, pure single phase iron oxide by just due to a high temperature the organic component of the dry gel is removed and we get a single phase iron oxide nanoparticle. So student, please note that there are also some advanced level of sol gel processed techniques available at which we can even get a single phase material at a low temperature, but in a conventional sol gel process the annealing temperature or sol gel annealing temperature or sintering temperature used in sol gel process is quite high. It's around 800 degrees centigrade to 900 degrees centigrade for ferrites. So different materials or different types of oxides have their own sintering and annealing temperature, so you have to consider the specific relevant temperature for those material if you want to prepare them by sol gel process. Like if you want to prepare a zinc oxide nanoparticle, they have their own specific temperature in order to reach to a single phase, whereas in case of iron oxide their temperature to reach to a single phase is between 800 degrees centigrade to 900 degrees centigrade for 30 to 1 hour. So, student, what do you think? What is the advantages of sol gel process? As I have previously discussed that the nanoparticles, nanomaterials or thin films may be prepared by wet chemical solution process, and some of the example of wet chemical solution processes are sol gel process, micro emulsion or million emulsion process, and chemical co-precipitation processes. And similarly, the thin films and nanomaterials may be prepared by high vacuum physical and chemical vapor deposition processes. So, dear student, both the solution based processes like sol gel processes and high vacuum based processes have some advantages and disadvantages. So in this lecture I will briefly explain about the advantages of sol gel process. Okay, so the student, the first advantage of sol gel process is that sol gel process is simple, economical and efficient method. Why do you think sol gel process is simple? Student, please note that in sol gel process we just need few beakers, pH meter, temperature measurement thermometers, and some uh, chemical salts and few acids and solvents. So we don't, and also we need a heating setup for sol gel processing. So in a simple word, we don't need any advanced setup for a sol gel process. So due to this, sol gel process is very simple. If we are preparing nanomaterials via advanced vacuum based techniques, there we need a highly advanced technology like a pressure controlling setups or high vacuum pumps, temperature controlling setups, and electron guns, and many more complex instrumentations. So, in the simple word, sol gel process is a simple process. Sol gel process is economical process. So the chemical precursor used in sol gel process, though they are costly, but still they are less costly as compared to the advanced synthesis routes of high vacuums. Okay, so the material used in sol gel processes are economical. Instrumentation of sol gel process is also economical, it is less costly. Another advantage of sol gel process is an efficient method. So basically we can produce an efficient materials with a sol gel process. The second advantage of the sol gel process is that sol gel processed materials or thin film have a high quality coverage. The material produced with the sol gel process are homogeneous and they are pure even at a low temperature. Now, this is very important advantage of sol gel process. So we basically get a high quality coverage via sol gel process. Basically we can prepare a thin film via sol gel process over the whole substrate. Okay, so basically we can disperse a chemical solution or wet gel onto the surface, onto the overall surface of the substrate. So basically, whole part of the substrate of surface may be covered by a sol gel processed wet gel. Okay, so the coverage of the substrate is usually done by spray coating or dip coating, um, uh, or spin coating of the sol gel processed solution. Another advantage of the sol gel process is that we can achieve a homogeneous, a uniform nanoparticles, thin films, nanowires and nanorods. So we can basically control a composition of the, by controlling the composition of initial precursors, we can basically achieve uniformity or homogeneity in composition by a sol gel process. And furthermore, we can also get a highly pure nanomaterials at a low temperature via sol gel process. Please note that at advanced level, usually the heating temperature is around 800 degrees centigrade to 900 degrees centigrade in sol gel processed thin films. However, in some cases they are in the range between 200 degrees centigrade to 800 degrees centigrade, and even between 100 degrees centigrade to 800 degrees centigrade. However, the temperature used in vacuum based setups is more than 800 degrees centigrade to between 1200 degrees centigrade. So the temperature is quite high, and due to this, but in the case of sol gel, we can get a same single phase material at very low temperature. Another advantage of the sol gel process is that with sol gel process we can produce ultra thin films, and these ultra thin films have an they have excellent adhesion between the substrate and the top layer, or between the substrate and the thin films. So student, what do you think, how we can achieve ultra thin film via sol gel process? This may be done by dip coating. In dip coating, if we decrease the number of dipping in a wet chemical sol gel solution, we can achieve a very ultra thin film. And similarly, if we increase the speed of the speed of the dipping, the time and the speed of the dipping, we can also achieve a very ultra fine thin film. Secondly, we can also use a spray coating to get an ultra thin films. Okay, in the spray coating, very fine layer of the wet sol gel is spray coated onto the surface of the substrate. Okay, and then it is dried, and at the end of the day we achieved the ultra thin film. So basically, the key advantage of the sol gel process is that we can produce ultra thin films via sol gel process. This ultra thin film is achieved by different types of coating methods which are used in sol gel process, like spray coating, dip coating and spin coating. And another aspect to consider is that the adhesion between the thin film which is deposited to the substrate is very good in a sol gel process. So this is the advantage of a sol gel process. Another advantage of sol gel process is that sol gel process is versatile. It is a diverse method, and versatile, and with the diversity of this method we can basically prepare a wide range of nanomaterials in the sol gel process. So basically we can use different types of, or even all kinds of transition metal in and we can produce their nanoparticles, thin films and nanorods and nanopillars by a sol gel process. And The versatility also of the solid gel process also include the control of the structure, and this process also control the porosity and the particle size. So the porosity is also a drawback of the sol gel process. Like when we coat it as wet sol gel onto the surface of the substrate, and with the annealing and sintering, there is a possibility of the porosity. So this porosity may be avoided, and it could be turned into an advantage by increasing the rate of the coating, or by increasing the thickness of the coated films and wet coated sol gel film, and by at the end, by heating and sintering, we basically get a less porous thin films. Sol gel process also control a particle. This control of particle is usually done by a pH value. It may be done by controlling the temperature of the solution during a sol gel process. It may be done by sintering and controlling the sintering and annealing temperature, and even it may be done by incorporation of the surfactant inside the sol gel solution. So now, dear student, another advantage of sol gel process is that we can produce a thick film via sol gel process, which can be used as a coating to protect the corrosion. Okay, so as I've discussed that we can produce a thick films by sol gel process, even like we are using spin coating, dip coating, or spray coating. We can increase the concentration of the chemical solution or wet chemical solution, and by increasing the concentration, like in case of dip coating, we can increase the number of the layer um, that should be deposited onto the surface of the substrate. By increasing the number of the layer, at the end of the day we get a thick film. Similarly, in a spray coating, we increase the rate of the spray coating onto the surface of the substrate. And similarly, in the spin coating, we basically decrease the rate of the spinning or the rotation, and increase the content of the wet chemical solution onto the surface of the substrate. So due to these physical methods, we basically achieve thick films. So these thick films are used in a different technologies, but they can also be used to protect a material. They may be used in a coating to protect a material against the protection. Okay. Another advantage of the sol gel process is that this process may be done around 200 degrees centigrade to 600 degrees centigrade. There are some research articles which are also illustrating that there are some ways in which sol gel process may be done around 100 degrees centigrade to 600 degrees centigrade. This means that the temperature of the sol gel process may be very low, and this method may be low temperature chemical solution processing method. So this is an advantage of the sol gel process, because the other types of methods for preparing the nanomaterials, like high vacuum methods, require very high temperature. So the advantage of sol gel process is that it may be a low temperature process. So this means that we don't need to reach to the melting temperature of the precursors materials. Okay, since the network structure can be achieved at relatively low temperature near the glass transition temperature. So this means that we don't, in some cases, if you want to operate a sol gel process of at a low temperature, we don't need to reach to the glass transition temperature, and even to the melting temperature of the precursor material. So this basically avoid the damage of the precursor material. and due to this advantage, at the end of the day we get highly pure nanomaterial. Students, please note that sol gel process do not require any type of expensive equipments. We just need a hot plate, some beakers, some chemical precursors, and thermometer and pH meter. So this process do not require advanced instrumental setup, and in a very low budget we can basically prepare nanomaterial and thin filmed via sol gel process. Dear student, okay, so in this lecture I will briefly explain about the few disadvantages of the sol gel process. One of the very important disadvantage of the sol gel process is a difficulty to avoid the residual porosity and OH groups. Okay, this is very important disadvantage of the sol gel process, and this is the reason that this process is less common in advanced technology or in advanced technological fabrication instruments or in microelectronic industry, because the sol gel process thin film usually they are porous. The porosity rate in a sol gel processed thin film is quite high because the wet sol gel solution, when they are deposited onto the surface of the substrate, is heated. So the wet part of the solution just get evaporated during the baking process, and whereas the organic part of the solid gel is just removed during the sintering and annealing part of the sol gel. So when the organic part and also the wet part of the sol gel solution is removed, there is a possibility of increase in a porous medium in nanomaterial which are processed by sol gel process. So the rate of the porosity in a sol gel process thin films and nanoparticle is too much, and this is the very important disadvantages which restrict a sol gel process to be used in microelectronic industries at advanced level. Another disadvantage of the sol gel process is the costly precursors. Usually the precursor salts, chlorides or nitrates, and the organic oxides used in sol gel process are very costly. So that is a disadvantage of the sol gel process. Another disadvantage of the sol gel process is long processing time. Students, please note that if we use high vacuum processes for nanomaterial synthesis, they take a few minutes to prepare a thin films or nanoparticles, whereas sol gel process require a longer time to prepare or to produce a thin film or nanoparticle. So sol gel process require aging time in order to achieve a single phase nanomaterial or thin film. Usually the processing during a chemical solution is done up to a few hours, and when we deposit the wet gel onto the surface of the substrate in thin films, they are baked for a few hours, and after baking the thin film or nanoparticles are sintered and annealed for few days. So this means that the sol gel process thin films or nanomaterials require longer time than the other high vacuum based techniques available. Another disadvantage of the sol gel process is the shrinkage of the wet gel upon the drying, which result into a fracture. Okay, So the structure of the film or nanoparticle which are achieved uh, from the wet gel are usually damaged in solder process, because when they are dried at higher temperature, they result into a stress in the structure, and there is a lot of porosity, and the structure is unstable. Due to this, the structure got damaged. So if I simply explain this disadvantage, usually in sol gel, if considered the thin film, we use a wet gel which is deposited onto the surface of the substrate. So this wet gel consists of a water molecule or a liquid molecule and also an organic components. Okay, so when this wet gel is baked, then the water molecule or solvent molecule are evaporated, and there is a possibility of porosity in the thin film. So these porous structures are unstable to the solid phase of the thin film, and when they are further annealed in order to achieve a single phase thin film, there is a possibility of increase in a stress inside the thin film, and due to increase in stress there is a possibility of a fracture in the thin film. So this is very important disadvantage of the sol gel process. This means that it is very difficult to achieve a highly uniform thin film in a periodic or in a continuous fashion in a sol gel process, because there is a possibility of damage or fracture or impurity in the or dislocation in the structure of the deposited thin film by a sol gel process. So now, students, another disadvantage of the sol gel process is used the organic solution used in sol gel process is usually toxic. It is hazardous. Okay, as you know that we especially in a polymeric route of sol gel process, we use metallic alk oxide and or alcohol and citric acids. Okay, so all these are may create a toxicity, and they are hazardous. Okay, so this is the disadvantage of the sol gel process. Another disadvantage of sol gel process is that the preferential precipitation of the particular oxide during the sol formation due to a different reactivity of alk oxide precursor may result into a destabilization. So this means that sol gel process require a preferential precipitations. Okay, and especially in a multi-component system. So there are some specific compositions or chemicals precursor. They have a preferential precipitation points, and they usually can effectively damage the chemical composition of the sol gel process thin films and nanomaterials. Let us discuss about the application of the sol gel process. So where the sol gel process is applied, please note that before going toward the application of sol gel process, we need to know that with the sol gel process, basically we can produce nanoparticles. Nanoparticles are the particles having a dimension or in the range between 1 to 100 nanometers. With the sol gel process, we can produce nano rods. Okay, their length is much, but in a few microns, but their diameter is around 1 to 100 nanometer. And with the sol gel process, we can also produce a nano wires. Okay, and similarly with the sol gel process, we basically produce a photonic crystals which they are used in optoelectronic industry. So it is different based on the physical structures like nanoparticles, nanorods, nanowires, and thin film prepared by a solvent process. These materials they may be used as ferroelectric materials. So basically, we can produce a ferroelectric materials via a sol gel process. Some of the most common example of the ferroelectric materials prepared by a sol gel process are barium titanate, okay, and similarly bismuth titanates are also reported that they may be prepared by a solvent process. So the room is quite diverse. With the solvent process, one we can basically prepare a ferroelectric material. Another application is that the solvent process may be used in preparation of the piezoelectric material. One of the most common piezoelectric material uh, prepared by a solvent process is known as zinc oxide. Usually, the zinc oxide nanorods are used and they are prepared by a solder process which are used in energy harvesting instruments. So, in a simple word, wide range of piezoelectric materials may be prepared by a sol gel process. Another application of solvent process is that we can prepare multiferric nanomaterials such as thin films, nanorods, nanoparticles via a sol gel process. One of the most commonly prepared multiferric material from a sol gel process is known as Arvelius phase multiferric materials. Okay, and the room of the solder process is not limited to ferroelectric or piezoelectric material, but multiferric materials may be prepared by a solder process. The student, please note that a solder process is also used in optoelectronic industry. Okay, so the solder process is also an essential part of the optoelectronic industry. Different types of optical instruments may be prepared by solder process. So basically in optical instrument, the thin films are usually produced or prepared by solder process. Another application of solder process is in hydrophobic industry. So hydrophobic materials are prepared by a sol gel process. Dear student, please note that it is also reported that reflective and anti-reflective coating setups are usually they are based on a silicon oxide layers. They are or they may be prepared by a sol gel process. So overall, please note that the sol gel process is very diverse. It is also a part of microelectronic industry, and it is also a part of optoelectronic industry. It is a universal technique for the synthesis of nanomaterials, which include nanoparticles, nanowires, nanorods, and thin films.